So let's take a look at a problem that we were going to try and do for homework. This triple integral here would be nice for spherical coordinates. You can see that right away because you have this x squared plus y squared plus z squared, and we know that equals rho squared. So right away we can start to rewrite this triple integral e to the square root of rho squared, which is just rho. Don't forget your correction factor for triple integrals, rho squared sine phi. And then we need to pick an order. So I'm going to do d rho, d phi, d theta. No particular reason why. Rho is going from 0 to 3, as phi goes from 0 to pi, and theta goes from 0 to 2 pi. So there we are. Let's go to work on this. So we first look at this integral. We look at the inside of it right here, this innermost piece. You notice you're integrating with respect to rho, which means sine phi is a theta, or I'm sorry, sine phi is a constant with respect to rho. So I'm going to put that out in front here, sine phi. Integral 0 to 3, e to the rho, and then times rho squared d rho. And we're in a little bit of trouble here. I don't know how bad it is, but I guess it depends on how you feel about integration by parts. You can tell this is an integration by parts problem because we have a product of two functions of rho, and the u substitution, which you typically do when you have e to a power, is usually let u equal the exponent. That's a fancy mu, sorry. Let's make it look like a u. Why not? So u, and then du d rho is just 1. And you'll notice that over here, I've still got that rho squared. And the fact that there's no variable here, I really needed a rho squared to show up here. The constant could have been different in front of it. Whatever number was in front of it wouldn't have mattered. But I needed a rho squared, and that does not happen. So a u substitution will not get you out of this. So that's how you kind of spot that this thing is an integration by parts, which you can think of as like the product rule in reverse, product rule for derivatives. Okay. And then also, in this particular case, you'll notice that rho squared has finitely many derivatives, and e to the rho does not, has infinitely many. This is a nice candidate for something called tabular integration by parts. And so how do you do that? It's not so bad, actually. You just take rho squared here, and then you write all its derivatives. So derivative of rho squared is 2 rho, and then you have derivative of that is 2, and then 0. And you take e to the rho, and you write all its antiderivatives. But those are easy because e is e to the x, and e to the rho are its own derivative and antiderivative. Sort of nice. And then the trick is this. You connect these things diagonally to make terms, and you alternate the sign in front. So this antiderivative becomes rho squared e to the rho. I'm getting that by multiplying this pair. Then you're going to have minus 2 rho e to the rho. That's what happens when you multiply this next pair. And you can kind of see what's happening. And so the last one's going to be plus 2e to the rho. So that's your antiderivative. It's going to need to be evaluated from 0 to 3. You know, every time I look at this procedure, it's sort of an amazing little trick. It's neat to check it. So you can check any antiderivative just by taking the derivative. So let's take the derivative of this thing and see how it works. So this right here, we take the derivative as product rule. I usually call this the first and this the second. So it's the product rule says you do the first function times the derivative of the second function plus the second function times the derivative of the first. And then we'll do this one also. This is also a product rule. So it's going to be minus everything in the parentheses here. First derivative of second plus second derivative of first. And then lastly, the derivative of that last term, derivative e to the p or e to the rho is just e to the rho times 2. So plus 2 e to the rho. And what's neat is this term cancels with that. And don't forget this negative would distribute over to here, and then these two would cancel, and you get exactly what we wanted. Which actually works. It's pretty amazing. Well, to watch it happen. Maybe not. Depends on your opinion, I guess. So let's go evaluate this. This page got cluttered, so let's go to another page here. So we have rho squared e to the rho minus 2 rho e to the rho plus 2 e to the rho, evaluated from 0 to 3. When we're done, we're going to have to multiply it by sine phi. We can't lose that constant. So if we put a 3 everywhere, we get 9e cubed minus 6e cubed plus 2e cubed. And then minus whatever happens when we plug in 0. When we plug in 0, this term will be 0 minus 0 plus 2 times e to the 0. E to the 0 is just 1, so you just get 2. So when everything's said and done here, these three terms combine, you get 9 minus 6 is 3 plus 2 is 5, so you get 5 e cubed plus 2 multiplied by sine of phi. Okay, so we got a little bit more work to do. Let's go look at that original triple integral. We're going to do d phi next from 0 to pi. So let's go do that. So here we are, integral 0 to pi d phi. Luckily, this crazy thing is just a constant, so we should take the antiderivative of sine phi, which is negative cosine phi from 0 to pi. If we plug in pi, we get negative cosine pi minus negative cosine 0. That'll turn out to be the negative of negative 1 plus 1, which is 2. So at this stage, we have 2 times e to the, oops, maybe a mistake there. Hold on a minute. We end up with times 5e to the third plus 2. The final antiderivative is to go from 0 to 2 pi with thetas, theta being the variable 0 to 2 pi. All right, so let's take that crazy constant. Where is it? There it is, that thing. We're going to integrate that. 2 times 5e cubed plus 2 d theta from 0 to 2 pi. But again, this is an easy problem because there's no thetas in here, so it's really just a constant. So the antiderivative, I'm just going to distribute this real quick, is 10e cubed plus 4 times theta evaluated from 0 to 2 pi. And we plug 2 pi in, we get 2 pi times that expression. We plug in 0, we get 0. So when you're all said and done, you just get 2 pi times 10e cubed plus 4. And that's as good as anything. You can just leave it like that. Okay, thanks for watching.